Hi, I'm Dan Bauer. Welcome to CBA Office Hours. It's an online forum where Patrick Kern and I talk about techniques and issues that arise in statistical analyses and behavioral health and social sciences. Today what I'm going to talk about is the linear regression model, and indeed the simplest linear regression model, a one-predictor linear regression model. This is going to be the start of a series of episodes on linear regression. And the reason why we chose to focus on the linear regression model is twofold. One, it's a very commonly used model in the health, behavioral, and social sciences. So we see it in many different applications, has a lot of flexibility. There are lots of things you can do with the linear regression model. The focus is typically on a continuous outcome variable as a function of one or more predictor variables. Those predictor variables typically are going to be continuous variables, but they could also include categorical variables that are included through coding variables. We'll also see how we can build in a variety of sorts of effects on the predictor side of the model. So widely used, but additionally a second reason why it's important to cover the linear regression model is that it's the foundation for many of the more advanced statistical techniques that we see often applied in the behavioral health and social sciences as well. So things like the structured equation model, factor analysis, generalized linear models, multi-level models, or mixed effects models. All of these are going to build off of the linear regression model as a starting point. And so it's useful to have a solid understanding of what that linear regression model is all about. All right, so just to get started today, what we're going to start out doing is making a distinction between what we're doing in statistical analyses, such as the linear regression model, and other kinds of relationships that were the focus of science earlier on in the history of science. So as an example, I'm going to use Newton's law of gravitation. And in Newton's law, we have a relationship between three input variables, three predictor variables, the mass of object 1, the mass of object 2, and the distance between them. So this might be the mass of the moon, the mass of the earth, and the distance between them. There's a gravitational constant, g, and if you plug those three variables in, n1, n2, and d, into this formula, then you get the force of gravity between those two objects. And the reason why I put this up there is I want to differentiate between this kind of relationship, which is a deterministic relationship, a perfect relationship, where if we know m1, m2, and d, we can calculate f, and a statistical relationship, the kinds of things we're looking at in linear regression, where we can't know exactly what someone's outcome value is going to be, but we can predict something about what it might be, what its expected level would be. Okay. So we're going to focus on these kinds of statistical relationships and how to characterize those with our data. All right, so as an example of the kind of relationship that we might be interested in, let's say that we've got an interest in how experience and performance relate to one another on a given task. And so our predictor variable x is going to be experience, and our outcome variable y is going to be performance. And we have a set of data on these two variables, and we want to characterize their relationship. Well, clearly there's a lot of variability here. Knowing someone's experience does not tell you perfectly what their performance is going to be. There are multiple individuals who have the same level of experience but different levels of performance. So it's not a functional, it's not a deterministic relationship in the same way as Newton's universal law of gravitation. Instead, we need to come up with some way of characterizing this relationship more statistically. So what can we say? Well, it looks like the level of performance tends to go up as the level of experience increases. Right? So we've got to grapple with the fact that every individual is unique, that there's inherent randomness in this data, that it's not a deterministic relationship. So we can't say exactly what someone's performance is going to be given their level of experience, but we could perhaps say what we would expect to see for an average individual with that level of experience. Right? So we could take a particular cross-section here, right? So we could say for this particular level of experience, there's going to be some distribution of values for performance, right? And that distribution of values is going to have some average level right there. And then if we took another cross-section right here, again, we would get some distribution of values, and that distribution would have some average level. So although we can't say anything we can't predict exactly where any particular individual score is going to be. We could say something about where we expect it to be, where the average level of performance would be as a function of experience. And in the regression model, that's essentially what we're trying to do, is we're trying to build a model that shows how the average or expected level of performance changes as a function of experience, right? And so what we're going to do is we're going to say, all right, so for a particular individual I, we can say their performance is yi. We expect their performance to be at some certain level that is a function of x, so some function of x, but then there's also going to be this inherent randomness captured by a residual or an error term, and we'll call that epsilon. So there's some function that characterizes this relationship for everybody in the population, f of x, but then for any given individual there's also this inherent randomness. All right, so for a given individual, we might expect to see their performance right there, but their actual score perhaps is up here, and that's that epsilon takes them away from that average. That's the part that we simply cannot explain. In the linear regression model, what we do is we say, well, that function, what we're going to do is we're going to use a straight line to characterize this relationship. So that's our f of x, right? Our f of x is going to be a straight line, and that's going to be equal to beta naught plus beta 1 x, right? A straight line is characterized by two parameters. So our y value is going to be equal to beta naught plus beta 1 x plus this epsilon, right? And this is the part that is the expected value of y given x, right? So this is what we can explain. This is what we feel like we understand, is how the mean of that distribution is changing. That expected value of y, expected level of performance, is changing as a function of experience. We believe that it's changing in a linear fashion as a function of experience. But then the epsilon is the part that we just don't know, right? We don't know what's causing that. That could be measurement error, that could be something unique to this particular individual, that could be because of other omitted predictors that would be important, such as aptitude, right? So there are a variety of things that are going to go into that epsilon term, but that is the piece that we simply don't know because every individual is unique. This is the part we focus on because this is where we say, well, this is what we understand, is we have some sense of how the mean of that probability distribution of performance is shifting as a function of our predictor. So the two primary parameters that we're interested in our regression model are beta naught and beta 1. Those are the two parameters we're most interested in. But there actually is a third parameter as well, and that's the variance of the residuals. So how much variance is there in those residuals, and we'll represent that by sigma square, and that's the variance of these distributions here, right? So there's a probability distribution for performance at any given level of experience, and the variance of that distribution is characterized by sigma squared, right? And we assume that variance to be the same at any given level of experience. That's the assumption of homoscedasticity. We'll talk more about that, or assumption of constant variance. We can talk more about that in a later episode. But we have these three parameters of interest, beta naught and beta 1. Those characterize how the mean of the distribution of y changes as a function of x, or is a function of x, a linear function of x. And then we have the variance of y given x, or the variance of those residuals, and that's the variance of the distribution at any given level of experience. All right, so we have these three parameters of interest. Now that's in a one predictor model. Obviously we could extend this model to include more predictors, and then we would have additional parameters of interest, and we'll see how we can do that in a subsequent episode of the office hours. But right now let's just focus on our interpretation of these parameters. Right, so we have beta naught and beta 1 are the parameters that govern the expected value of y, or the mean level of y that we would expect to observe at any given level of x. So the average performance for a given level of experience. All right, so we can say the expected value of y when x is equal to some particular value. All right, so y given x, so this little pipe indicates given x, has some particular value, is going to be beta naught plus beta 1 x, right? And so now what we want to say is, all right, how do we interpret that beta naught and beta 1? Well, let's say we're interested in y when x is 0, right? So someone who has 0 experience, then we would have beta naught plus beta 1 times 0, and beta 1 times 0, of course, then is just going to drop out. Anything times 0 goes away. And so we now have our interpretation of the intercept. Our intercept is interpreted as the expected value y when x is 0. In this case, that would be the expected level of performance. So let's say 0 is right here. Beta naught would be the expected level of performance when experience is 0. So where that regression line crosses the y-axis, where x is 0, that's beta naught. All right, but what happens as experience goes up, right? So we can say, well, what about if someone has 1 year of experience, let's say? Then we'd have beta naught plus beta 1. What happens if someone has 2 years of experience? Then we have beta naught plus beta 1 times 2. And notice that for every 1 unit increase in x, we get a beta 1 unit increase in y. Our interpretation of the slope, the beta 1 parameter, is it's the change in y that we expect to observe for a 1 unit change in x. Right? So for a 1 unit change in x, we get a beta 1 unit change in y. It's the slope. It's the rise over run, going back to middle school or junior high geometry. It's how much change do we expect to observe in our outcome, our y variable performance, given a 1 unit change in our predictor, our x variable. All right, so in a subsequent episode, we'll talk a little bit more about how do we obtain estimates of our model parameters, right? So we have beta naught and beta 1 that we need to estimate. We also have sigma square, our residual variance that we're going to estimate. So how do we obtain estimates of those parameters? We'll talk a little bit more about ordinary least squares and how ordinary least squares work. That's the predominantly used estimator, although there are other ways of estimating regression models as well. But we obtain estimates of those regression parameters based on our sample data. We'll also talk about how do we use those estimates to make inferences about the population parameters and so forth. But for right now, we really just want to focus on the basics of interpretation. So what is beta naught? What is beta 1? How do we interpret those? How is this a useful way of characterizing the relationship between two variables? So next we're going to turn to a demonstration, and we'll see this in practice.
Okay, so this is the data we're going to play around with a little bit. It consists of 16 individuals, 16 undergraduates at Ohio State University who participated in a study looking at the relationship between alcohol consumption, psychomotor impairment, blood alcohol content, and so forth. And so each of these individuals, they recorded their sex and weight. They were randomly assigned a number of 8-ounce beers to consume, between 1 and 9 beers. Their blood alcohol content, their blood alcohol concentration was measured, presumably using a breathalyzer. This is typically measured in grams per deciliter. As some points of reference, in North Carolina, where I live, the legal limit is 0.08 for standard driving, although if you are a commercial driver, so for instance like driving a truck or something, then the legal limit is 0.04 for that. And then first sober and second sober are road sobriety test scores before and after the consumption of the beers. Now we're going to focus exclusively on the two variables beers and BAC, and we're going to look at how BAC changes as a function of number of beers consumed. We would expect that alcohol consumption would cause blood alcohol concentrations to rise. So beers is a causal or explanatory variable leading to potential changes in the distribution of BAC values. We would expect mean BAC to increase with beers consumed. These other variables, we might think, some of these other variables we might think would have some relationship to BAC. So for instance, your body weight might influence your BAC even at a given number of beers. So, you know, unfortunately, just as an unhappy chance of randomization, the one person assigned 9 beers to drink was a 110-pound female. We might expect, just based on conventional wisdom alone, that her BAC might be elevated relative to what would have happened had that 9 beers been assumed to the 275-pound male. So we're going to ignore these other variables, and of course by ignoring them, any variation that they would otherwise account for will go into the residual term, that error term epsilon. And we could, you know, in subsequent models, we could build out our regression model to include these as additional predictors. But for right now, we're going to focus on the simple regression model with just the one predictor, so beers predicting BAC. Let's take a look at the scatter plot of those two variables. You can see that here. And so you see a nice, strong relationship, as you might expect, between amount of beers consumed and BAC. Remember, beers are 8-ounce beers. That's about 1/4 of a liter. That's a smaller amount than would be a typical serving size at a bar or in a bottle. And then BAC, the legal limit is 0.08, so that's indicated with a reference line here. And you can see there's a nice strong relationship and a relatively linear looking relationship. It looks like BAC is increasing in a fairly linear way. This particular observation might be slightly elevated. That's our 110-pound female. But it looks like a fairly linear relationship. So let's drop a regression line in there. So here's our regression line, and you can see, it does track the points pretty well. It seems like a fairly linear relationship. We also see in the lower left here our regression equation. This is telling us the intercept, this negative 0.012701, we'll say negative 0.013, rounding a bit. That's our intercept. Remember, that's our expected level of BAC given 0 beers, expected level of the outcome when the predictor is 0. And then here's our slope, 0.017964, we'll say 0.018, rounding up a little bit. And so for each additional 8-ounce beer consumed, we expect BAC levels to increase by 0.018 on average, right? So it's that expected level of BAC that follows this linear trend, but of course there's scatter around that. So even if the expected level of BAC is below 0.08 at 4 beers or even 5 beers, given the scatter around that, given that randomness, that part that we can't explain, no guarantee that you would be under the legal limit even at 4 beers, but certainly at 5 beers, some of the observations appear to be over that. Now again, our interpretation of these is fairly straightforward. The intercept is a little bit tricky because we don't actually see it in the plot. We don't have 0 beers indicated here. So I'm going to just extend our plot out a little bit to show where that 0 beers is. And so here I've just changed this x-axis to go all the way out to 0. So there's our intercept, is negative 0.0127, negative 0.013. So that's our estimate of beta naught right there. And then our estimate of beta 1 is 0.018, and that's the increase that we expect to see between 0 and 1, between 1 and 2, between 2 and 3. For every 1 unit increase in beers consumed, we expect to see a 0.018 increase in blood alcohol content. We can also see that by calculating the predicted values given by this regression line. So what would we expect to see at 0, 1, 2, 3, 4 beers on up? And so I'm just going to calculate those and print those out for us to have a look at. So here they are. At 0 beers, there's our intercept, negative 0.013. Remember, your intercept is wherever the predictor is 0. And then with 1 beer, it goes up by 0.018. With 2 beers, it goes up by another 0.018. With 3 beers, it goes up by another 0.018. And so you can see if you were a commercial driver at 3 beers, 3 8-ounce beers, you'd be expected to be over the legal limit. But perhaps even with 2 beers, you might, if you account for the fact that that's just the expected value, there is variation around that. And then for the standard legal limit, 5 beers is just under that for the expected value. But again, of course, remember there's scatter around the line. So with 4 beers, you might not be safe either. And keep in mind, these are 8-ounce beers, whereas the typical serving size is larger. But this just gives you an idea of what that linear regression model does. It's giving you an intercept that sort of starts the line out. Where does the line begin when the predictor is 0? And then that slope tells you how that line is increasing over time, the rate of increase in BAC per unit increase in number of beers consumed. So hopefully that just gives you a sense of how these models might be used in practice and how to interpret the parameters of the regression model.
So that's it for our episode of Office Hours for today. Just to recap, we've considered the linear regression model with a single predictor. We have a continuous outcome, we have a continuous predictor, and we're looking at the relationship between those using a linear function. Our goal is to explain how the mean of the distribution of the outcome, so in this case the mean of the blood alcohol concentration levels, changes linearly as a function of the predictor, so as a function of number of beers consumed. And using that linear function, we have two parameters of primary interest. We have an intercept, beta naught, we have a slope, beta 1. We obtain estimates of those and we make our interpretations as we described, the intercept being the expected value where the predictor is 0, and the slope being the expected increase or change in the outcome per unit increase in the predictor. So that's our simple linear regression model. In subsequent episodes, we'll talk about a variety of additional issues such as estimation and inference, how to extend the linear regression model to include multiple predictors, how that influences our interpretation of slopes, and we can talk about the incorporation of categorical predictors and a variety of other topics. Thank you very much for your attention for today, and we'll see you next time.